The emptiest parts of space hold a secret more powerful than all the stars. This apparent void, the vacuum between galaxies, may contain more energy than every single star, planet, and galaxy combined. You are about to learn exactly how this is possible and why it redefines our understanding of reality itself. We will venture into the heart of modern physics to uncover how empty space is actually a seething sea of potential, driven by bizarre quantum behavior and a mysterious force accelerating the cosmos. How do you visualize nothingness when it might be the source of everything? Aristotle's conviction that nature despises a vacuum held sway for nearly 2,000 years. He believed a true void was an impossibility, that the cosmos was a continuous plenum, a substance filling every gap. This idea was so powerful it shaped scientific thought for centuries. Then came James Clerk Maxwell in the 1800s, whose elegant equations described light not as a mere particle, but as a wave. This posed a profound question. A wave needs something to wave in. Sound needs air, ocean waves need water. So what medium was light rippling through as it crossed the vast emptiness of space? Scientists proposed the luminiferous ether, an invisible, frictionless substance permeating the entire universe, acting as the stage for light's performance. This was the final stand for the idea of a filled space, but experiments, most famously the Michelson-Morley experiment, went looking for this ether and found absolutely nothing. The stage, it seemed, was truly empty. This failure was not an end but a beginning. It forced a radical rethink, leading to a young patent clerk named Albert Einstein. His theory of special relativity did away with the ether entirely. It showed that light does not need a medium. Space and time themselves were not a static stage, but were woven together into a single, dynamic fabric. This fabric could warp and curve, telling planets how to move and light how to bend. The void was no longer a passive container. It was an active participant in the cosmos. Yet this new vision of space-time, for all its grandeur, was still essentially empty. It was a clean geometric stage. The true shock, the one that would shatter the very meaning of nothing, was brewing in the frantic, hidden world of the atom. The quantum revolution was about to reveal that the vacuum is not just a fabric, but a seething, chaotic sea. Einstein's elegant fabric of space-time was about to be torn apart at the seams. The quantum revolution revealed a universe where certainty was an illusion, governed by a rule that reshapes reality itself, the Heisenberg Uncertainty Principle. This principle states a fundamental truth about our cosmos. You cannot know everything at once. For any particle, its exact energy and the exact moment you measure it form one of these forbidden pairs. The more precisely you pin down one, the more wildly uncertain the other becomes. This is not a limitation of our machines. It is a built-in feature of the universe. And it has a staggering consequence for the void. It means that a perfect total zero of energy is impossible. Emptiness cannot be still. For fleeting instants smaller than any measurable time, the void can borrow energy, so long as it pays it back almost immediately. This cosmic loan sharking gives birth to something from nothing. Pairs of particles and their antimatter twins, virtual particles, boil into existence from the pure potential of the vacuum. They flicker for a mere moment before they collide and vanish, returning their borrowed energy to the bank of nothingness. This is not just a mathematical curiosity. We can see its fingerprint in a lab. Take two perfectly smooth, uncharged metal plates and place them incredibly close together in a vacuum, only a few atoms' width apart. In the gap between them, only certain types of virtual particles can appear, those whose wavelengths fit perfectly in that tiny space. But outside the plates, in the wider vacuum, a riot of virtual particles of all sizes can bloom. This imbalance creates a subtle pressure pushing the plates together. This is the Casimir effect, a measurable force born from the ghostly dance of particles appearing from nothing. So the vacuum is not empty. It is a stormy, frothing sea of creation and destruction, a vibrant arena where the very concept of nothing has lost its meaning. And this quantum groundwork is just the beginning of the vacuum's true power. So we have a force born from nothing. That gentle, irresistible pull between two plates in a vacuum is not some theoretical ghost. It is a real, measurable pressure, a whisper from the quantum world that we can now hear loud and clear. This is the Casimir effect in action. Picture those two perfectly smooth, uncharged metal plates placed just nanometers apart, a gap smaller than a single bacterium. In our everyday classical view, an utter vacuum between them should be just that, empty. There should be nothing to push or pull, yet the plates are drawn together as if by an invisible hand. What is truly pushing them? The answer lies in the nature of the void itself. In the vast, open space outside the plates, the quantum vacuum is a chaotic marketplace. Virtual particles of all shapes and sizes, all possible wavelengths, are constantly flickering in and out of existence. But in the narrow gap between the plates, it is as if only certain vendors are allowed to set up shop. Only those virtual particles whose wavelengths fit perfectly within that tiny space can appear. This creates a dramatic imbalance. The riot of activity outside the plates exerts more pressure than the limited selection of activity between them. The result is a net force pushing the plates together. It is not that something magical is happening in the gap. It is that the gap restricts the wild energy of the vacuum while the outside does not. The nothingness outside is literally more forceful than the constrained nothingness inside. This was not just a brilliant prediction by Dutch physicist Hendrik Casimir in 1948. It has been confirmed with stunning precision in modern laboratories, leaving no doubt about its quantum origin. The Casimir force is our most direct bridge. It connects the dizzying mathematics of quantum field theory to a phenomenon you can, in principle, feel with your own hand. It proves that the vacuum is not a passive stage but an active, roiling energy field. Emptiness, it turns out, has a palpable push. This ghostly pressure from the void is just a tiny whisper of the vacuum's true voice. If you could listen even closer, you would hear a deeper, more fundamental hum, a vibration that never, ever stops. This is the ground state of the universe itself, a concept known as zero-point energy. Picture the strange world of a quantum particle, like an electron bound to an atom. Even if you could cool the entire universe down to absolute zero, the coldest temperature possible where all classical motion is supposed to freeze, this electron would not be still. It would continue to jitter and vibrate, possessed by a minimum energy it can never shed. This is not a matter of heat, it is a fundamental rule. A quantum particle can never be completely at rest. It always possesses this residual, irreducible energy, its 0 point. Now take that single jittering particle and expand the idea to encompass everything. The universe is not filled with just a few particles, but with fundamental quantum fields. These are the bedrock of reality, and like the electron, every single one of these fields has its own 0 point energy, a perpetual, unstoppable hum. When you add it all up, the energy contained in every single cubic centimeter of seemingly empty space becomes a number so vast it defies human comprehension. Some of the simplest calculations in physics suggest the energy density of the vacuum should be over 10 to the power of 120 times greater than the energy we actually observe in the cosmos from all the stars and galaxies combined. That number is not just large, it is arguably the greatest mismatch between theory and observation in the entire history of science. This colossal problem is known as the cosmological constant problem, and it represents a screaming void in our understanding of physics. The vacuum, this apparent nothingness, is theoretically packed with more power than we can possibly conceive, a silent storm of infinite potential whose true nature remains one of our universe's most profound and unsettling secrets. That staggering mismatch between theory and observation was a problem so profound it seemed to break physics. Yet the universe had already provided a clue, one that a brilliant mind had discovered and then famously thrown away. Albert Einstein, while crafting his masterpiece of general relativity, faced a problem. His equations beautifully described how matter and energy warp space-time, creating the force of gravity. But they also predicted a universe that should be either expanding or contracting. The scientific consensus of his day, however, insisted the cosmos was eternal and static. To force his theory to match this belief, Einstein introduced a mathematical fix, a fudge factor he called the cosmological constant. This was a repulsive energy, a kind of anti-gravity woven into the very fabric of space itself, designed to perfectly balance the inward pull of gravity and keep the universe still. Years later, when Edwin Hubble's observations proved the universe was indeed expanding, Einstein realized his mistake. He had allowed the fashion of the day to override the pure logic of his own equations. He discarded the cosmological constant, calling it his greatest blunder. For decades, it was treated as a scientific relic, a cautionary tale about doubting your own math. But the story was far from over. In the late 1990s, two independent teams of astronomers were studying distant stellar explosions, supernova, to measure how fast the universe was expanding. They expected to find that the pull of gravity from all the galaxies was slowing the cosmic expansion down. Instead, they discovered the exact opposite. The expansion of the universe was not slowing at all. It was speeding up. Some mysterious, repulsive force was overwhelming gravity itself, pushing galaxies apart at an ever-increasing rate. This discovery of cosmic acceleration was so shocking it won the Nobel Prize. And what was the simplest, most elegant explanation for this repulsive force? A positive cosmological constant. Einstein's greatest blunder was not a mistake after all. It was a prediction decades ahead of its time. The energy of the vacuum, that seething quantum hum, was not just a theoretical ghost. It was real, and it was shaping the entire cosmos. The void itself, the energy of empty space, was acting as a constant, relentless pressure, stretching the universe apart. So the cosmological constant provides our most direct link. It connects the frantic, microscopic quantum world of virtual particles to the grandest scale imaginable, the ultimate fate of everything. The energy hidden in nothing is literally steering the evolution of the entire universe. The discovery that reshaped our cosmos was not made by peering at the void, but by staring into the hearts of dying stars. Across unimaginable distances, astronomers tracked the faint glow of supernova, cosmic mile markers that revealed a universe fleeing from itself. The data was undeniable. The expansion of the cosmos was not merely continuing, it was accelerating, as if space itself were stretching faster with every passing moment. This revelation was so profound it earned the Nobel Prize in Physics in 2011. And it introduced us to the universe's dominant hidden player, dark energy. This mysterious force makes up a staggering 68% of everything that is. Think of that for a moment. All the stars in every galaxy, all the planets, every human, every atom you have ever seen or touched, constitutes less than 5% of the cosmos. Dark energy, the force of the vacuum, is more than 13 times greater than all of it combined. The simplest explanation, the one that fits our current models, is Einstein's cosmological constant, the energy of empty space itself. If this is correct, then the true ruler of the cosmos is not matter but the void, those immense black deserts between galaxies, which we dismissed as barren emptiness, are in fact the primary engine of cosmic evolution. Their silent, repulsive energy is actively pushing the universe apart, overwhelming the collective gravity of all creation, yet its true nature remains one of our greatest enigmas. Is dark energy truly constant, a fixed property of the vacuum woven into space-time itself? Or is it something more fluid, a dynamic field that could change over billions of years, perhaps even fading away or growing stronger? Answering this question is the driving force behind the most ambitious astronomical projects of our time, from immense ground-based telescopes to space observatories designed to map the history of expansion with exquisite precision. The fate of everything, whether the universe will expand forever into a cold, dark silence or be torn apart in a final cosmic rip, hinges on the answer. The energy of nothing has been thrust from the fringes of physics to the very center of our quest to understand reality. This fundamental shift in perspective is the key to unlocking the vacuum's secret power. Quantum field theory asks us to stop thinking of the universe as a collection of tiny balls in a void, and instead to see it as an ocean of invisible, fundamental fields. These fields are not made of anything else. They are the most basic ingredients of reality, and they exist everywhere at all times. There is an electron field that permeates all of space. There is a quark field, a Higgs field, and fields for every known force and particle. What we call a particle, like a single electron, is not a solitary speck. It is simply a localized excitation, a tiny knot of vibration in the everywhere present electron field. Think of it like the surface of a calm pond. The pond itself is the field. A particle is not a separate object floating on the pond, but a ripple moving across its surface. Now, what happens when the pond is perfectly calm, with no ripples at all? In our old way of thinking, that would be true emptiness, but in quantum field theory, even this perfect calm possesses a deep, thrumming energy. This is the zero-point energy, the absolute minimum vibration these fields can have. They can never be completely still. The void is not the absence of the fields. The void is the fields, all of them, in their ground state. This means that every single cubic centimeter of space, from the depths of intergalactic space to the air in front of you, is a site of immense, seething potential. It is a broth of fluctuating energy where virtual particles constantly blink in and out of existence as temporary excitations of these underlying fields. This framework gives physicists the mathematical language to ask a simple, profound question: how much energy is actually stored in this universal ground state? When they perform the calculation, the result is a number so catastrophically large it vaporizes all common sense. The predicted energy density is greater than the total energy of all matter in the observable universe by a factor of 1 followed by 120 zeros. This is not a small error. It is the most spectacular failure of a prediction in the history of science. The framework that so beautifully explains the behavior of every known particle also insists that the energy of empty space should be so immense that it would have ripped the universe apart in a fraction of a second after the Big Bang. Clearly, something is deeply wrong, or we are profoundly missing a crucial piece of the puzzle. This staggering mismatch of 120 orders of magnitude is known as the Vacuum Catastrophe. It stands as the single greatest failure of a prediction in all of science. To even begin to grasp the scale of this error, picture the entire observable universe, every single galaxy and star packed with energy. Now take that immense total and understand that the vacuum energy predicted by our best quantum theories is a number so much larger it is like comparing the entire cosmos to a single, solitary subatomic particle. The reality we observe is that whisper, that single particle, while the theory screams an entire universe. If the vacuum truly held even a fraction of that naive prediction, the consequences would have been instantaneous and absolute. The repulsive force of space itself would have been so titanic that it would have overcome every other force in nature at the moment of the Big Bang. Gravity, the nuclear forces, even electromagnetism would have been utterly irrelevant. No atoms could have ever bonded, no stars could have ever ignited. The universe would have exploded into a formless, accelerating fog of disconnected particles, freezing into absolute isolation in a fraction of a second. There would be no planets, no life, and no one to ask these questions. The simple, undeniable fact of our own existence, of a structured and stable cosmos, is the ultimate proof that something is deeply wrong with this calculation. The vacuum catastrophe is not a minor accounting error. It is a screaming siren that our two most successful theories, quantum field theory and general relativity, are fundamentally incompatible when it comes to the energy of nothing. They are telling two completely different stories about the same universe. This glaring mismatch is our most important clue, a signpost pointing toward a deeper layer of reality. A theory that can finally reconcile the frantic quantum world with the serene cosmic expanse. The vacuum catastrophe screams for a new law of physics, a principle that can tame the infinite energy of nothing. One of the most elegant proposals comes from a theory known as supersymmetry. Its core idea is one of profound cosmic balance. It suggests that for every particle we know, from the humble electron to the quirky quark, there exists a hidden super partner. Imagine a cosmic dance where every dancer has a perfect mirror, a shadow with a slightly different step. In this beautiful symmetry, the frantic quantum jitter of a particle and the jitter of its super partner would be exact opposites. Their contributions to the vacuum's energy would cancel one another out, like two perfectly matched waves that meet and create a calm sea. This cancellation could solve everything, reducing the catastrophic prediction of 120 orders of magnitude down to a small, manageable number, perhaps even to zero. The universe would be stable because its underlying structure is perfectly balanced. For this perfect cancellation to work, however, the symmetry must be unbroken. The superpartners would need to have the same mass as the particles we know. If that were true, we should have found them by now. Our most powerful machine, the Large Hadron Collider, has been searching for these shadows. It has smashed protons together at energies that should have effortlessly produced them. So far, it has found nothing. The silence from the collider is deafening. This means that if supersymmetry is real, it is a broken symmetry. The superpartners, if they exist at all, must be immensely heavier than their standard counterparts. And in that broken state, the beautiful, perfect cancellation is ruined. The delicate balance is shattered, and the vacuum catastrophe roars back to life. Yet, the theory remains so mathematically compelling that the search continues. It represents a path not yet fully closed, a whisper of cosmic order that might still be discovered at even higher energies, a ghost in the machine of reality that could still hold the key to the power of the void. Another field, however, is definitely not zero. The Higgs field permeates every corner of the cosmos, an invisible ocean we are all swimming through. Its sole purpose is to give mass to the universe's fundamental building blocks. Without it, particles like electrons and quarks would zip around at the speed of light, weightless and unable to form atoms, stars, or us. Its discovery in 2012 confirmed a monumental piece of our cosmic story. But the Higgs field holds a deeper secret about the void. Unlike some quantum fields that can truly quiet down to a perfect zero, the Higgs field is always on. Even in its lowest possible energy state, what we would call empty space, it has a constant non-zero value. It is like a spring that is permanently compressed, storing energy just by existing. This means the Higgs field is a direct, confirmed contributor to the energy of the vacuum. It is not a virtual particle or a theoretical ghost. It is a real, measured component of nothingness. Yet, when physicists calculate how much energy this ever-present field should be adding to the cosmos, they run straight into the fine-tuning problem. The energy density from the Higgs field is significant, but it is still unimaginably smaller than the catastrophic sum of all quantum fields. It is as if the universe has performed a calculation with 120 digits and then somehow, almost magically, cancelled itself out to leave only the tiniest whisper of a result, the dark energy we detect. The Higgs field gives us a real number to work with, a concrete piece of the vacuum energy puzzle. But instead of solving the mystery, it deepens it immensely. Why does the universe exhibit such incredible precision? How do the frantic contributions of countless fields balance with such delicate perfection to leave behind just the faint repulsive force we observe? The Higgs mechanism shows us a concrete example of energy in the void, but it makes the overall silence of the vacuum seem even more like a carefully guarded secret. This primordial burst of energy offers a stunning glimpse of the void's ultimate power. The theory of cosmic inflation rewinds the clock to the universe's first fleeting moments, to a time so early that the very concepts of particles and forces had not yet congealed. In that first sliver of a second, the cosmos was likely dominated by a hypothetical field known as the inflaton field. Crucially, this field was trapped. It was not in its true, stable, lowest energy state, but was stuck in a false vacuum, a configuration of immensely high energy. Think of a ball resting precariously on the peak of a very high hill, when the true valley of lowest energy lies far below. The energy density of this false vacuum state was unimaginable, and according to Einstein's equations, such a dense energy woven into space itself produces a powerfully repulsive form of gravity. This repulsion did not just push matter apart, it stretched the very fabric of space-time. The universe did not simply expand, it underwent an exponential explosion, doubling in size repeatedly in intervals of time so short they are almost meaningless to us. In less than a millionth of a billionth of a billionth of a billionth of a second, a subatomic speck of primordial reality was blown up to a scale larger than our entire observable universe today. This superluminal expansion, faster than light itself, was not matter moving through space, but space itself being created at a ferocious rate. This single, breathtaking event solved multiple cosmic puzzles in one stroke. It explains why the universe appears so remarkably flat and uniform in every direction we look. The violent stretching ironed out any initial wrinkles and curved any initial warping, leaving behind the smooth, vast cosmos we observe. Then, as abruptly as it began, inflation ended. The inflaton field, unstable in its high energy state, finally rolled down the hill, settling into the true vacuum valley we likely inhabit today. In that process of decay, the colossal energy stored in the false vacuum was released in a cataclysmic flash, flooding the universe with a hot soup of particles and radiation. igniting the traditional Big Bang. Here is the profound lesson. The energy that drove this most transformative event in all of cosmic history was not the energy of stars or matter. It was the energy of a field trapped in a false state of nothingness. The vacuum, or something very much like it, was the engine of creation, proving that the energy of empty space is not a passive background hum. It can be the active, dynamic force that forges the entire structure of reality, setting the stage for everything that was to come. The ghostly presence of virtual particles leaves its mark on the very heart of an atom. Within the simple hydrogen atom, a single electron orbits a single proton. According to the pure classical theory of quantum mechanics, this electron should occupy very specific, precise energy levels. But when Willis Lamb and his colleague Robert Rutherford investigated this in the 1940s, they found a subtle discrepancy. One of these energy levels was slightly shifted from where it should be, as if an invisible hand was gently nudging the electron. This tiny split, this Lamb shift, was a profound mystery. The explanation lies in the restless vacuum. The electron is not orbiting in perfect, empty space. It is constantly buffeted by the sea of virtual particles flickering in and out of existence around it. This interaction subtly alters the electron's energy, changing its orbit by a minuscule amount. The Lamb shift is not a dramatic force, but it is a measurable one, a direct fingerprint of the vacuum's energy on the most fundamental structures in nature. This same quantum whispering reshapes our understanding of the most powerful objects in the cosmos. At the edge of a black hole, where gravity is so intense that not even light can escape, the vacuum performs a stunning trick. Just outside the event horizon, the point of no return, virtual particle pairs constantly emerge from the void. Normally, these pairs annihilate each other almost instantly. But here, the black hole's immense gravity can intervene. It can pull one particle of the pair across the horizon, trapping it forever, while its partner escapes into space as a real particle. This process, known as Hawking radiation, slowly drains energy and therefore mass from the black hole, causing it to evaporate over astronomical time scales. The energy for this entire process is borrowed from the gravitational field of the black hole itself, but it is facilitated by the virtual particle pairs of the quantum vacuum. The void is not just tweaking atoms, it is slowly dismantling the most formidable prisons in the universe. Perhaps the most precise validation comes from the magnetic heartbeat of an electron. Quantum electrodynamics, our most accurate physical theory, relies entirely on the concept of virtual particles to explain the electron's magnetic moment. The calculations involve summing up an infinite series of possibilities, diagrams where the electron emits and reabsorbs virtual photons and other particles. When physicists perform these incredibly complex calculations, the theoretical prediction for the electron's magnetism matches the experimentally measured value to more than 10 decimal places. This is an agreement of breathtaking precision, and it would be utterly impossible without accounting for the ghostly influence of these transient entities. So while we can never trap a virtual particle in a box, we can see its shadow everywhere. Its effects are etched into the energy of atoms, they glow from the edges of black holes, and they are encoded in the most fundamental properties of matter. This is the ultimate confirmation that the vacuum is a dynamic medium, a cauldron of potential whose energy content is not a mathematical fiction. It is a fundamental, active ingredient in the recipe of reality, shaping the universe from the infinitesimal to the cosmic. But these ghostly whispers from the void are just echoes of a far deeper chaos. To find the true source of the vacuum's immense energy, we must journey to the very limits of reality, to a scale so small it defies visualization. This is the domain of the quantum foam, Imagine the smooth fabric of space-time as predicted by Einstein's general relativity. Now, shrink your perspective down to the Planck length, a distance so minuscule that a single proton would be as large in comparison as a star is to that proton. At this ultimate frontier, the serene cosmic stage dissolves into a seething, turbulent froth. The geometry of space-time itself is no longer smooth and predictable. It is subject to such violent quantum fluctuations that microscopic wormholes and tunnels blink in and out of existence. The very concepts of cause and effect, of before and after, lose all meaning. In this frenzied sea, the idea of a single, continuous location becomes meaningless. This chaotic substratum was first envisioned by physicist John Wheeler, who gave it its evocative name. The energy tied up in this frantic churning of the fabric of reality itself is beyond colossal. It is, in fact, the primary suspect in the vacuum energy catastrophe. Every fluctuation in this foam represents a massive warp in space-time geometry, and each warp carries an enormous gravitational energy. The problem is when we try to add up this gravitational contribution from the quantum foam to the total energy of the void, the result is that same impossible number, that one with 120 zeros. This is the heart of the problem. Our current theory of gravity, general relativity, and our theory of the quantum world simply cannot both be correct at this scale. They give contradictory, nonsensical answers. To truly understand the energy of nothing, we need a theory that can describe this foam, a theory of quantum gravity that can marry Einstein's cosmic stage with the frantic quantum dancers performing upon it. Until we can peer into this ultimate chaos and see its rules, the deepest wellspring of the vacuum's power will remain a beautiful, turbulent mystery. Faced with this cosmic coincidence, a startling question emerges. Why does our universe possess such an impossibly perfect balance? One controversial answer points the finger not at the cosmos but directly back at us. This is the Anthropic Principle, a line of reasoning that suggests the universe's constants are tuned for a simple, profound reason. We are here to observe them. The logic is stark. If the vacuum energy were even slightly larger, the repulsive force would have been so overwhelming that galaxies, stars, and planets could never have coalesced from the primordial gas. The universe would be a cold, empty, and accelerating void. In such a cosmos, there would be no one to wonder about its emptiness. We exist, therefore we must inhabit one of the rare, perhaps even unique, universes where the numbers just happen to work out. This idea finds a powerful home in the concept of the multiverse. Picture a vast cosmic landscape, an infinite froth of bubbling universes, each born with its own random set of physical laws and constants. In most of these universes, the cosmological constant is a catastrophic number, rendering them sterile and lifeless. But in an exceptionally tiny fraction, by pure chance, the vacuum energy is minuscule. We are not privileged observers of a finely tuned cosmos. We are simply the inevitable inhabitants of one of the few universes capable of producing observers at all. This is not a physical explanation that describes a mechanism or a force. It is a statistical argument. It does not tell us how the cancellation occurs, only that our presence here is conditional upon it having occurred. For many scientists, this is deeply unsatisfying. It can feel like giving up on a fundamental explanation, retreating into a philosophical stance where anything is possible somewhere. Yet, for others, it provides the only coherent framework for a puzzle that has resisted all other solutions. The energy of the void, then, might not be a problem to be solved by our equations, but a fundamental condition of our existence, a silent, fixed boundary of reality that makes our own story possible. This silent, statistical argument forces a radical shift in our search for answers. If we cannot yet derive the vacuum's energy from first principles, perhaps we can catch it in the act, measuring its subtle effects with ever more ingenious experiments. The quest is to move from philosophical possibility to physical proof, and scientists are building tools of breathtaking sensitivity to do exactly that. In laboratories around the world, researchers are refining measurements of the Casimir effect, no longer just confirming its existence, but probing its precise behavior at different distances and with different materials. They are searching for any tiny deviation from the predicted force, any anomaly that could signal a new, undiscovered force or a hidden property of the quantum vacuum itself. Another frontier lies in the heart of the atom itself. Atom interferometry experiments use the wave-like nature of atoms as exquisitely fine sensors. They are looking for minuscule, rhythmic changes in the fundamental constants of nature, like the fine structure constant that governs the strength of electromagnetic interactions. The idea is that if dark energy is a dynamic field and not a true constant, its fluctuations could cause these universal numbers to wobble imperceptibly over time. Detecting such a wobble would be a revolution, proving that the energy of the void is alive and changing, but the most ambitious probes are looking out at the cosmos. The European Space Agency's Euclid Telescope and NASA's upcoming Nancy Grace Roman Space Telescope are not simply cameras. They are cosmic cartographers designed to map the history of the universe's expansion over billions of years. By observing billions of galaxies and thousands of distant supernovae, they will measure the subtle tug of war between gravity and dark energy with a precision never before possible. Their goal is to answer the fundamental question: is the strength of dark energy truly constant, or has it evolved over the life of the cosmos? The answer will determine the ultimate fate of everything. Simultaneously, particle smashers are looking inward. The Large Hadron Collider and the designs for future, even more powerful colliders are hunting for any crack in our current theories. They seek new, exotic particles or evidence of supersymmetry or hidden dimensions, any phenomenon that could provide a natural mechanism for the near-zero value of the cosmological constant. Every one of these experiments, from the lab bench to the edge of the observable universe, shares a single purpose: to find a deviation. They are all searching for a single crack in the perfect, smooth facade of our current models. The discovery of even the smallest anomaly would be a floodlight in the dark, illuminating the path toward the deeper theory that must lie beyond, a theory that can finally tell us why nothing holds the key to everything. This energetic void forces a complete redefinition of reality itself. For millennia, Western philosophy has been built upon a clear distinction, a binary split between being and non-being, between something and nothing. The ancient Greek philosopher Parmenides argued that nothingness could not even be spoken of, for to speak of it was to grant it a kind of existence. This idea echoes through the ages, shaping our instinct that a true vacuum must be inert, a passive stage, but the quantum vacuum shatters this ancient dichotomy. If the dominant energy in the cosmos comes from what we once called emptiness, then being quite literally arises from non-being. The universe is not a collection of objects in an empty container. It is a dynamic, inseparable whole where the container and the content are woven from the same energetic fabric. The stage itself is the most active performer. This radical notion finds a powerful echo in Eastern traditions, particularly in the Buddhist concept of sunyata, often translated as emptiness. This is not a bleak, nihilistic void. It is a fertile ground of potential, a state of open, dependent origination from which all phenomena arise. The quantum vacuum, in its ceaseless creation and annihilation of virtual particles, is a stunning scientific parallel to this philosophical insight. It is a plenum of latent existence, a fullness disguised as absence. In the West, the phrase creatio ex nihilo, creation out of nothing, has long been a theological cornerstone. Modern physics does not invoke a creator, but it does ground this concept in physical law. The universe, in its earliest moments of inflationary expansion, was quite literally driven by the energy of a false vacuum, a state of rich non-being that gave rise to all the something we see today. The line between nothing and something is not a sharp boundary but a blurred, permeable membrane. This re-evaluation reaches far beyond the laboratory. If the very foundation of reality is a creative, dynamic process rather than a static collection of things, it challenges our most basic assumptions about permanence and substance. We are not isolated beings on a rock flying through dead space. We are temporary patterns, intricate knots of vibration, emerging from and returning to an energetic ground that is more fundamental than matter itself. The emptiness between stars is not a desolate wasteland. It is the source, the silent, generative heart of everything. This silent background energy might even dictate the direction of time itself. Our everyday experience tells us time flows in one direction, from a definite past toward an uncertain future. We remember yesterday, but not tomorrow. A cup shatters on the floor, but the pieces never spontaneously reassemble themselves. This one-way street is known as the arrow of time, and its ultimate source is a concept called entropy. Entropy is essentially the universe's measure of disorder, and a fundamental law states that the total entropy of the cosmos can only ever increase or stay the same. It never decreases. Think of a drop of ink diffusing in a glass of water. It starts in an ordered, low-entropy state, a single dark spot. Then it spreads out, mixing randomly until the water is uniformly tinted, a state of maximum disorder and high entropy. The process is irreversible. The scattered ink molecules will never spontaneously gather back into a single, neat drop. This relentless march toward disorder is what gives time its arrow. Now connect this to the expanding vacuum. As dark energy pushes galaxies apart, the universe grows vastly larger, colder, and emptier. With more space, there are exponentially more ways for all the energy and matter in the universe to be arranged in a disordered, scattered state. The expansion itself is constantly opening up new possibilities for chaos, driving the entropy of the cosmos ever higher. In the far, far future, this process reaches its logical conclusion in a state cosmologists call heat death. All stars will have burned out, all black holes evaporated. The universe will be a thin, cold, and perfectly uniform soup of particles and radiation, stretched across an unimaginable void. In this final equilibrium, entropy has reached its maximum value. No energy differences exist anywhere to perform any work. No processes can occur, and time, as we understand it, may effectively cease to have any meaning. The relentless push of vacuum energy creates the expanding stage upon which the cosmic drama of increasing entropy plays out. Without this expansion, the arrow of time might not point so decisively forward. The energy of empty space, therefore, is not just stretching the cosmos. It is the silent conductor orchestrating the irreversible flow of time from the past into the future, linking the ultimate fate of the universe to our most fundamental experience of reality. The holographic principle turns our intuition about space inside out. It proposes a radical limit to how much information any region of space can possibly hold. This idea was born from a deep puzzle about black holes. When an object falls into a black hole, it seemingly vanishes, taking all its information with it. But this violates a core tenet of quantum mechanics. Information, it is thought, can never be truly destroyed. The brilliant resolution, pioneered by physicists like Jacob Bekenstein and Stephen Hawking, was that a black hole's information content is not stored in its vast, mysterious interior. Instead, it is perfectly encoded on its two-dimensional surface, the event horizon. The entropy, the ultimate information capacity of the black hole, is proportional to the area of this boundary, not the volume it encloses. This was a stunning departure from everything we thought we knew, where information capacity always scales with volume. Think of it this way: the information needed to describe everything inside a room, every dust mote, every air molecule, every possible event, could be written like a hologram on the walls of the room itself. The three-dimensional world we experience could be a projection from a two-dimensional surface at its boundary. This is the holographic principle, and it forces us to abandon the idea of locality, the notion that everything that happens is determined by interactions in immediate local space. The universe, it suggests, is fundamentally non-local. Its deepest workings are written on a distant, lower-dimensional screen. How does this shatter the vacuum catastrophe? Our naive quantum field theory calculation that predicts an infinite vacuum energy assumes that every single point in space is an independent, fundamental degree of freedom. It treats space as an infinitely divisible continuum with an unlimited number of tiny oscillators at every location, all humming with zero-point energy. But if the holographic principle is true, the number of true, fundamental degrees of freedom in any volume is not proportional to the volume. It is proportional to the surface area. The number of independent bits of information that can exist inside a sphere is limited by the area of that sphere in Planck units. This is an immense reduction. For a large region of space, the volume grows much faster than the surface area. A naive calculation for a 1 meter cube might assume a number of degrees of freedom proportional to the cube of its dimensions. The holographic bound says the true number is proportional only to the square. This cuts the available energy states for the vacuum down by an astronomical factor. While it may not yet precisely yield the tiny cosmological constant we observe, it points the way toward a natural resolution. The vacuum cannot store an infinite amount of energy because space itself has a finite information density. The holographic principle imposes a cosmic data limit, preventing the void from holding the catastrophic energy our old math predicted. It suggests that the true nature of reality is not what we see in the volume around us, but is written on a distant, fundamental surface we have only just begun to imagine. This cosmic battery was forged in the first moments of everything. During the Big Bang, the universe's unimaginably hot, dense birth likely locked a staggering amount of energy into the very fabric of space itself, creating a reservoir of power on a scale we can barely comprehend. Think of the vacuum not as a void, but as a fully charged cosmic cell, a battery manufactured at the dawn of time. This battery's energy is not static. As the universe expands, creating more and more volume of space, it is as if we are adding more and more battery cells to the cosmic grid, each one pre-charged with this latent vacuum energy. The cosmological constant, the simplest form of dark energy, acts like a perfect, unending trickle charge. It ensures that as new space is created, it comes with the same intrinsic energy density, perpetually powering the acceleration of the cosmos. In this scenario, the battery's lifetime is essentially infinite. It will never run down, forever driving galaxies apart into an ever-cooling, ever-expanding future. But what if our understanding is incomplete? The history of our universe provides a dramatic precedent for a battery that can discharge. The inflattened field that powered cosmic inflation was a perfect example of a high-energy vacuum state that was not stable. It was a battery with a finite, if enormous, charge. When it decayed, it released all of its pent-up energy in a flash, reheating the universe and igniting the hot Big Bang. If dark energy is a similar dynamic field, rather than a true constant, then our current cosmic battery could also be slowly depleting. Its repulsive power might fade over billions of years, allowing gravity to once again take the reins. Or, more catastrophically, it could decay suddenly, releasing its energy in a second transformative event that would rewrite the laws of physics in an instant. The total capacity of this vacuum battery and its eventual fate are the central questions defining our cosmic destiny. Will the universe continue its lonely, accelerating expansion forever, or will this foundational power source one day flicker and die, leading to a future we can scarcely predict? The answer depends entirely on whether the energy of nothing is a permanent feature of reality, or just another temporary phase in an ever-changing cosmos. That cosmic battery may be the ultimate power source, but drawing even a single watt from it is a problem that defies our current laws of physics. Science fiction paints visions of starships powered by the void itself, yet reality presents a wall of fundamental obstacles. The first is a profound paradox of location. This energy is not concentrated in some distant nebula or at the core of a star. It is perfectly, uniformly smeared across all of existence. The vacuum energy is the same in the deepest void between galaxies as it is in the air right in front of you. There is no mine to dig, no reservoir to tap. You cannot point to a source because the source is everywhere at once and therefore effectively nowhere specific. This uniform distribution makes it useless for performing work. Think of a perfectly flat pond stretching to the horizon in every direction. There is no water flowing from a higher point to a lower one, so you could not possibly build a water wheel to extract energy. The vacuum is that flat pond on a cosmic scale. Any engine, any machine we can conceive of, requires a difference in energy, a gradient to drive a process. The vacuum, in its pristine state, offers no such handle. The second, even more fundamental barrier is thermodynamic. The vacuum's immense energy density represents the ground state of the universe, the absolute lowest energy level that the quantum fields can have. This is the cosmic baseline. Extracting useful work from a system in its ground state is like trying to get a ball to roll downhill when it is already at the very bottom of the valley. According to the unbreakable laws of thermodynamics, it is impossible. To get energy out, you would have to lower the energy of the vacuum in one region even further, creating a new, lower ground state. We have no idea how to do that, and the consequences of trying could be cataclysmic. Concentrating or manipulating vacuum energy in a localized area would require warping space-time with unimaginable intensity. Such an experiment could easily create a region of space so warped that it collapses into a tiny black hole, swallowing the apparatus and potentially radiating dangerously. The Casimir effect proves we can influence the vacuum, yes, but that influence merely reshuffles the existing energy, creating a temporary, minuscule imbalance. It does not extract net energy from the system. We are like children on the shore of an infinite ocean, able to create tiny ripples but possessing no cup to take a drink. The chasm between knowing the energy is there and actually being able to use it is perhaps the widest in all of modern physics. A humbling reminder that the universe's greatest treasures may be forever locked away by the very laws that make them possible. This cosmic tug-of-war defines the architecture of everything we see. On one side, dark energy relentlessly pushes the universe apart, stretching the cosmic fabric. On the other, dark matter exerts a powerful gravitational pull, acting as the invisible skeleton upon which galaxies are built. It is dark matter's gravity that initially gathered the primordial gas, allowing it to collapse into the first stars and the majestic galaxies we observe today. Without this unseen anchor, the universe would be a formless, accelerating mist with no structures to speak of. Dark matter makes up roughly 27% of the cosmos, a silent, dominant presence that sculpts the cosmos on the grandest scales. The battle between these two giants, one pushing and one pulling, dictates the fate of cosmic structures. Galaxies within a cluster are bound together by dark matter's glue, resisting the dark energy trying to tear them apart. Yet, on the vast intergalactic scales, dark energy is winning, accelerating the expansion and determining the ultimate destiny of the universe. This fundamental opposition raises a profound question. Are dark energy and dark matter truly separate entities, or could they be two faces of the same mysterious coin? Some physicists are exploring theories that attempt to unify them. One compelling, though highly speculative, idea involves a dynamic quantum field known as quintessence. Unlike a static cosmological constant, quintessence is a fluid-like energy that can change over time and space. In this model, the behavior of this single field could vary dramatically. In the dense, crowded regions of space within galaxy clusters, the field might clump and behave gravitationally like dark matter, providing the glue that holds structures together. But in the immense, empty voids between galaxies, the same field could smooth out and exert a negative pressure, acting just like the repulsive force of dark energy. This would mean the vacuum's energy and the universe's invisible mass are not isolated phenomena. They could be deeply intertwined, different expressions of a single, underlying substance that we have not yet discovered. While quintessence remains a theoretical possibility without direct evidence, its appeal lies in its potential to solve two of cosmology's greatest puzzles at once. It represents a bold step toward a more complete picture, one where the energy of nothing is not an anomaly, but an integral part of a unified cosmic drama. This silent acceleration is already writing the final chapter of our cosmos. If the vacuum energy remains a constant force, the future it dictates is one of profound isolation. In roughly 100 billion years, the expansion of space will have carried every galaxy beyond our local group over the cosmic horizon. They will not simply fade away like distant ships sailing into the night. Their light, stretched beyond detection, will cease to reach us entirely. The universe outside our immediate galactic neighborhood will vanish from all possible observation, leaving our descendants, should any exist, with a sky almost devoid of external galaxies. The grand tapestry of the cosmos will have been torn away, leaving only a local, isolated thread. Star formation will be the next great cosmic process to end. The interstellar gas and dust that fuel the birth of new stars will be gradually locked away in dead stellar remnants, or dispersed so widely by expansion that new stars can no longer coalesce. The last flickers of nuclear fusion will cease, and the galaxies will darken one by one. Over timescales that dwarf the current age of the universe, even the mightiest black holes, the last bastions of structure, will succumb. Through the slow, relentless trickle of Hawking radiation, they will leak away their mass, eventually vanishing in a final, silent flash. What remains is a universe approaching a state known as heat death. This is not a fiery explosion, but the ultimate cold. The cosmos becomes a vast, dark, and nearly perfect void, where the temperature everywhere drifts infinitely close to absolute zero. All energy is evenly distributed, with no hot spots or cold spots left to drive any process. No stars shine, no planets orbit, and no complex structures of any kind can exist. In this final equilibrium, the only significant feature left is the vacuum energy itself. Its constant, repulsive density becomes the sole defining characteristic of reality. The latent energy of empty space, which today is an invisible background actor, will become the final and only player on the cosmic stage. This is the ultimate triumph of emptiness, a bleak but fascinating destiny where the void we have explored becomes the entire story. The very struggle to measure the ghostly whisper of the Casimir force has sculpted the tools of our modern world. To detect such a subtle pressure, scientists were forced to invent instruments of almost unbelievable sensitivity, mastering the manipulation of matter on the scale of nanometers. This relentless drive for precision did not stay locked in a physics lab. It became the foundation for the entire field of nanotechnology and the micro-electromechanical systems, or MEMS, that now power our daily lives. The accelerometer in your smartphone that knows when you tilt the screen, the tiny mirrors that project light in a digital projector, the microscopic sensors monitoring our health, all these technologies were honed by the same need to control and measure forces in the realm of the vanishingly small, a capability born from our attempt to listen to the quantum vacuum. Beyond the hardware, the theoretical puzzle of vacuum energy has forced mathematicians and physicists to forge entirely new computational weapons. The mathematics required to even approach the vacuum catastrophe are so complex they demand, and have spurred the creation of revolutionary algorithms and computing methods. These tools now ripple outward, finding unexpected applications in fields like cryptography and data analysis, strengthening the entire edifice of our digital civilization. Perhaps the most profound spin-off lies in the quest for a theory of quantum gravity itself. The desperate need to reconcile the quantum world with Einstein's space-time has not just given us string theory or loop quantum gravity. The struggle has gifted us with deep conceptual breakthroughs in seemingly unrelated areas. Our understanding of exotic states of matter, like superconductors and superfluids, has been dramatically enriched by ideas developed for quantum gravity. The entire field of quantum information science, with its promise of quantum computers, draws heavily from the same well of deep spacetime concepts. So while a vacuum energy engine may forever remain a dream, the intellectual journey to understand it is already paying immense dividends. It proves that aiming for the most distant, fundamental targets does not just expand our abstract knowledge. It builds the very tools, the mathematics, and the conceptual frameworks that transform our world in the most practical and unexpected ways, rewarding our curiosity with a richer reality. Our journey ends with a universe transformed. The void is not an absence but a presence. That apparent emptiness is the most energy-rich substance we have ever encountered, a dynamic sea whose hidden rules govern the ultimate fate of everything. It is the quantum jitter at the heart of every atom, the ghostly pressure in a vacuum chamber, and the silent, repulsive force accelerating the cosmos. The vacuum is not the backdrop, it is a lead actor in the cosmic story, and the vacuum catastrophe, that staggering mismatch between prediction and reality, is not a failure. It is our brightest beacon, a glaring signpost screaming that a deeper layer of physics awaits discovery, one that will finally unite the quantum world with gravity. This exploration shatters the ancient line between something and nothing. It forces us to see that existence itself arises from a fertile ground of potential, a vibrant emptiness more fundamental than matter. The universe's greatest secret was never hidden in a distant galaxy. It was here all along, woven into the fabric of space itself, a testament to the boundless, humbling wonder of physical reality. If this journey has reshaped your view of the cosmos, we would love to hear your thoughts in the comments below. Subscribe for more voyages into the heart of existence, where the next great mystery is always waiting.